Okay, so now let's look at the important case of retractions on embedded manifolds, in particular where the embedding space is again a vector space, always a vector space. Okay, so this is retractions on embedded submanifolds. Okay, so let M be an embedded submanifold of a vector space. Let's call that E. Right, then in that situation, the tangent space at X, it's like of M, can be viewed as a linear subspace of the tangent space at X of the vector space E. And of course, as before, it's like the tangent space at a particular point, it's like of a vector space can be canonically identified with that vector space again, right? And yeah, this can be identified with E. All right, so so what that allows you to do then is that through this identification, you can do this abuse of notation where, well, not really abuse of notation, but you can, yeah, well, you can sort of essentially add a vector to a point on the space, right? And of course, you know, that's something which we tend to do all the time without really thinking about it on linear spaces. But it's again important to realize that there is this essentially canonical identification, which you're really doing. It's like when you try to do something like that. Okay, so then by an abuse of notation, right, we can consider the sum sort of x plus c, right, of a point x on the manifold M and c in the tangent space at x of M, and then this thing should be viewed as an element of the tangent space of the vector space. Actually, no. Okay. Yeah, okay. So what I want to do is that I want to think of this as being embedded in the tangent space to E, and then sort of identified with E, right? And then something similar happens here. M is embedded in E by the inclusion, and so essentially what happens is that when you say x plus c, right, you can't do that on the manifold M, but M has a natural inclusion. It's like into the vector space. So I can think of x as a point on the vector space, and I think I can think of c, it's like as being included into the tangent space to the to the vector space E. It's like which then is identified. It's like with E itself, right? So both of these things then can be viewed as elements of the vector space E. Okay, and of course when that happens, then I can use the vector space structure. It's like to talk about the addition. Okay, so so this thing is viewed as an element of the vector space E. Okay, all right. So so if you do that, then it's you know, tempting to try to construct a retraction with this in mind, right? So maybe let's draw a picture. It's like so that you know, you have a better idea what's going on. You have x again. It's like which is on the manifold M. This is contained in some sort of embedding space. This is Tx M. There's a vector here, right? And I'm just doing sort of the obvious thing I would normally do if I was in the embedding space, which is I look at x, I take x plus c. This is a point which is you can think of as being in this, still in this tangent space, right? But sort of usually off the manifold M itself. Okay. So once you do that, if you want to define a retraction, which is now a map from the tangent space to the manifold, it's like back to the manifold itself, you might want to have some sort of projection back onto the manifold. Okay. So so the point is that it is tempting to construct a retraction on an embedded manifold M, right, by the following feature, right? So the first thing is that, so you move along this vector, right, to the point x plus c, right, in the embedding space, and then you project the point x plus c back to the manifold M, and then the composition of these two things, it's like would then give you something which plays the role of a retraction. Okay, so the challenge, right? So the challenge is to define a projection so that the composition right yields an actual retraction, which is to say that it satisfies, you know, the two properties of retraction, right? So the first property is not so hard, right? Because the first property is that if the vector is 0, it's like you add 0 to it, you still get x. And then if your x is already on the manifold M, it's like, you know, the usual types of projections. It's like would mean that you don't want to move it. So so the composition of these two things with sort of a projection which is sort of fairly natural, which is to say that if it already is in a manifold, you don't change it, right? Then the composition of those two things, it's like would obviously satisfy the first condition of a retraction, which is to map the 0 vector to the base point. Okay. The second condition then is potentially more difficult, which is this local rigidity condition. Okay. So let me sort of remark how that can be done. So the remark is that the second condition, the local rigidity condition, can be sort of satisfied by using projections sort of based on matrix decompositions. Well, I mean, again, it's like, so for the purposes of this class, we're primarily focusing, it's like on matrix manifolds, right? So in many cases, it's like there are various types of matrix decompositions, it's like which one can take advantage of. So for example, QR factorization, and sort of polar decompositions. All right. So but let's try to you know, see what conditions it's like we can establish. It's like more generally, it's like on this projection, it's like so that it has this local rigidity condition. Okay, so all right. Okay, so let's say, as before, that M is an embedded manifold, be an embedded manifold, right, of a vector space E, and N be an abstract manifold with the property that it is complementary dimension. Okay, such that the dimension of M plus the dimension of N is the dimension of the vector space E. Okay, then you assume that there's a diffeomorphism what you sort of would expect is that there's a diffeomorphism from the product of these two manifolds, M and N, to the vector space. Okay. And here I'm just going to map it to E star. It's like which is just some sort of open subset, right? And there's sort of something like an identity element in this manifold N. Let's call it I in N, such that when you have this diffeomorphism for a point F and a point I, where I is this neutral element in N, right, you just get F, right? So for all F in M. So that's more or less saying that this map, it's like with some unknown thing, and the identity is just the identity map on M, right? Okay. All right. So if you have that, and then the reason why we choose this, we call this identity element I is because, well, actually, is because it's going to turn out to be the case that this is oftentimes the identity matrix. Okay. And then in the context of this earlier remark about matrix decompositions, right, this diffeomorphism, if you will, is oftentimes, so say if M and N are these Q and R factors, it's like in the QR decomposition or in the QR factorization, and then this is the the general linear group, right? This map from here to here is usually just matrix multiplication. And then if it's matrix multiplication and the second factor is the identity, then obviously F times I is just F itself, right? So that's how this sort of more abstract framework, right, relates to the stuff which I had sort of alluded to earlier. It's like about these projections being based on matrix decompositions. So the basic idea then is that if you have a general matrix here, you do the matrix factorization to the two parts, and then one of these pieces is the one which is in the space you want it to be in. So say for polar decompositions, it's like one of the factors is a rotation matrix, so you can use the polar decomposition to give you a projection, say, back onto the space of rotation matrices. Okay. All right, so in any case, you have this sort of diffeomorphism, and again, I've sort of given you a sense as to how this is related to what we know. It's like, it's like from matrix factorizations. Okay, so let me state the proposition now. So under these assumptions, on this diffeomorphism, right, the mapping Rx of C, which is defined to be pi 1. Right, so the idea is that you take, what's going to happen is that you take the inverse of this diffeomorphism to give you the factors m and n, and then you project onto the part which is m, right? So this is where the pi 1 is. If you have pi 1 acting on m cross n, right? So let's just say that pi 1 acting on m cross m and n is just m, right? That's basically what's happening here. Okay, so pi 1, it's like the inverse of the diffeomorphism applied to x plus c. Okay, so x is a point in the manifold, because c is a vector-based vector. It's like at the point x, I've identified, I've embedded both of these two things into the vector space E. I've identified the tangent spaces of E. It's like with itself, so I can add these two things together. So this is an element of E. I take the inverse. This gives me now something in M cross N, and I project it into M, right? So that's sort of a natural choice for this retraction, right? So this thing, again, where pi 1 is a map from M cross N to M, right? Where you take M cross N and you map it to just M, right, is a projection onto the first component. Right, that defines a retraction. On M. Okay. Yeah, so in order to prove this, it's like one basically has to show that this map I've defined here satisfies the two properties of a retraction, right? And in particular, the harder property to show is that there's a local rigidity property. Okay. So let me not prove it, but let me sort of just remark the following, that the critical aspect of this map, right, which is used to show there's a local rigidity property, is exactly this condition that so the remark is that the essential property of this diffeomorphism, right, that allows one to prove the local rigidity property is that is the existence of this neutral identity element, right? Is that okay? So, and let me sort of remark further that where you use this, okay, is that when you take f of I and you take its inverse by this diffeomorphism, and then you take its projection, right, you just get F. Okay, so right, so that's really sort of where so you use this condition, right, and then essentially you linearize it in order to show that you have a, so you linearize this to sort of establish the local rigidity condition. Okay. All right. So again, I don't really want to go too much into the details of it, but suffice to say that it's like the forward map. It's like of this usually is just in most of these matrix factorization questions is really just matrix multiplication. So the inverse map is the one which is usually hard to compute, right? So this inverse map is the one which is usually hard to compute. It's like that's the part which involves this matrix factorization algorithm, say QR, say polar decomposition. And then once you have that, then you project onto the appropriate piece which is relevant for your problem. Okay, so let me just stop here for now.